Today in Honors Physics, we'll be looking at how a slinky falls and why. First, we'll take a look at the forces acting on each ring of a slinky, and afterwards, we'll take a look at how these forces change after you drop it.
None of the rings are moving, so we'll start with the bottom ring. The sum of the forces on the bottom ring must be 0 in order for the ring not to move. We have a force of gravity downward, and thus we must have a force of tension equal in magnitude but opposite direction pulling upward. On the second ring, there's a force of gravity pulling downward, and notice there's a force of tension pulling downward as well. And this force of tension pulling downward is equal in magnitude but opposite in direction from the force of tension pulling upward on the first ring. These two forces of tension are, in fact, equal and opposite reaction pairs. So that's important because if this force of tension changes for some reason, it will impact this force of tension. They will both change. So we can draw the force body diagrams up through up for each ring of the slinky until we get to the top ring. We see that this force of tension acting downward on the top ring is is the same force of tension acting upward on the second to last ring. So when this force of tension, or the force exerted by the hand disappears, the forces acting on the top ring are only the force of gravity and the force of tension. And as the ring begins to accelerate, the distance between the top ring and the second to last ring decreases. Thus, the force of tension here will decrease, which will make this force of tension decrease, and so on and so forth down the slinky. This chain reaction would indicate that the slinky would fall all at once, and not as it does in reality, where the bottom doesn't move. Mark will explain to you why this is the case.
We've marked the top ring, the upper middle ring, the lower middle ring, and the bottom ring. We wanted to use Logger Pro and video analysis to see how each individual ring falls as Jacqueline lets go of the top ring. We see that the top ring falls first, while the upper middle ring waits for it until the top ring has already hit it, and then it falls together. And then once it reaches the middle ring, then it falls together again. And then at the same time, the lower middle ring has been waiting the entire time, and then falls once the system has propagated through. And that's the same as the bottom ring, and that is why it stays still the entire time. And once the entire system has fallen through, then the bottom ring falls.
When the slinky starts to fall, the force of the hand goes away, and the top ring is just left, FG and FT pulling the slinky downward. As this distance between the top ring and the second ring starts to decrease, both this FT and this FT start to decrease, which we would expect to cause a instantaneous chain reaction going down the slinky. However, as we just examined in the video and in the graph, this is not the case. And there's a problem with our assumption that we made when making these free body diagrams that indicates where a problem might lie. We treated the slinky as a system of separate rings connected by something like rubber bands. But in reality, the slinky is one continuous medium. And this causes the change in force present on the top ring to affect the rest of the slinky in a wave-like pattern, as you could kind of see in the previous video, when the top of the slinky starts to bunch up and bunch up and bunch up, as if it was a sound wave or something like that coming out of my mouth, and there are large changes of pressure.
The key to thinking about the slinky falling like a wave is to imagine how it moves laterally. For example, if you make a wave in the slinky while it lies horizontally, as in the video, you can see that the movement propagates as a wave. In order for a point on the slinky to move, the point before it has to move and pull on it.
This same idea holds true for a slinky being held vertically and dropped. Let's call this point point A. Point A can't fall until the point directly above point A has fallen, because point A is attached to the point directly above it, and therefore its movement is determined by the movement of the point directly above it. This means that the slinky must fall ring by ring, since no one point can fall until the point above it has fallen.
So when the slinky is dropped and it begins to fall ring by ring, the distance between any two rings will not change until all the points above it have fallen, or the rings above it have fallen. Therefore, the tension holding up any single ring won't change until all the rings above it have fallen, and therefore that ring itself will not fall until all the rings above it have fallen.
Thus concludes our video on why a slinky falls the way it does. First, there's uneven distribution in slinky, and that causes the upwards tension to be equal to the downwards tension plus force of gravity. Secondly, the tension force change must propagate through the slinky, and only until then will the suspended rings begin to fall. And thus we see the lower rings always suspended until the top ring has fallen down onto it.